Welcome to the fifth industrial revolution. Life is interesting, isn't it? Climate crisis, energy crisis. Every day we are hearing more and more alarming news. The news that means a lot of the land we live on will be underwater. A lot of land where we produce food may not be available for that because we'll need land to live somewhere. Energy crisis, food crisis, you name it. Maybe the news is just about selling bad news, but at the same time, the climate crisis more and more is real, right? So what does that mean? What that means is life on Earth 50, 100, 200 years from now will look very different than it looks today. What it will look like, we don't know, but that's the trend line. On the other hand, can't open the news these days without reading one more story about our adventures in space, whether it is about a new satellite in space, whether it is about, a new space treaty or some new investment or another startup looking for funding to figure out how they can either mine in space or create another satellite system that helps with life in space. So another trend line, becoming a big business. Last we heard $1 trillion industry as well. So another trend line. The commonality in both of these trend lines, the human body, the human race. And the human race, unfortunately, is neither adept at living in drastically different environmental circumstances on Earth, nor in space. So how do we solve for this quandary? Is health technology going to be the defining force for the future and maybe the fifth industrial revolution? So that's our thesis. And today, it is really a great pleasure to welcome Dr. Kris Lehnhardt. And Kris, I will just read a little bit of your bio here. So Dr. Lehnhardt is the element scientist for exploration medical capability at the NASA Johnson Space Center. He's a board certified physician in emergency medicine, I believe both in US and Canada. And he's a senior faculty with the Baylor College of Medicine at their Center for Space Medicine and Department of Emergency Medicine. I also understand you work at the emergency department at the Bentop Hospital in Houston.
That's correct.
What did I miss?
Not much. I think that all I would add to that is my work at NASA in exploration medical capability is part of something called the Human Research Program.
Okay.
And the job or the goal of the Human Research Program is to help NASA to develop all of the technologies and capabilities necessary for humans to explore beyond low Earth orbit. So beyond the space station and on to the moon and Mars. So our goal is to try and help push humanity deeper into space and living and working in deep space for longer and longer periods of time.
Wonderful. That is certainly, something you would think of when watching Star Trek and, think science fiction, but we now know it is way beyond science fiction. So what got you interested? I mean, how does an emergency physician get into space medicine?
It's a great question. I have always been what I would affectionately call a big space nerd.
Yeah.
So I've loved rocket launches since I was a little kid. I've always been fascinated by human space flight, and space shuttle missions in particular were really interesting to me when I was young. And so as a result, as I was going through my schooling and realizing that I really enjoyed the biological sciences, I tried to find a way to align my interests in space with my interest in biology. And being a kid growing up in a small town in Canada, I didn't have a lot of references to people who were in the space industry, but I knew astronauts. And so looking at the profiles of Canadian astronauts, one of them, his name is Dave Williams. He was an emergency physician.
Okay.
And he went to space. And so I thought, maybe this is my opportunity to get involved in space and space activities. So I pursued a career in emergency medicine as a result.
Oh, okay. So it was an inspiration that led you to do this.
Yeah.
Oh, wonderful. So my wife is a physician, and I have a lot of physician friends. And when I look at all of them, they train in a pretty, defined environment and train on humans living on Earth. How do you train to be a physician for someone who's going to be in space?
It's a challenge, frankly. And in the United States, there are some formal training programs for aerospace medicine. But in Canada and in many other countries around the world, those types of formal training opportunities don't exist. So in essence, what I had to do was to create my own pathway to space medicine. And so what I did is I focused on the medicine of extreme environments. Or how do you provide medical care to people in difficult circumstances?
I see.
And so that includes not only the aerospace environment, but also diving medicine. It incorporates elements of wilderness medicine, as well as disaster medicine. And so when there's a natural disaster, for example, you may have a lack of access to definitive healthcare. You may have a lack of resources at your disposal, and you may be very much on your own, meaning that there isn't necessarily someone else you can call or who can come and help you. And so those principles related to extreme environmental medicine are where I focused my attention. So I learned about the medicine of improvisation, and I learned about the medicine of the different environments and how your anatomy and physiology changes in each of these environments.
Right.
And all of those opportunities I used to build up my knowledge and experience in the medical field, in that medical field. And now my work is applying that information and that knowledge to how we're going to provide medical care for astronauts during exploration missions.
So you make a very interesting point, which is, you are learning about how to take care of people in space by understanding how you can take care of people on Earth in very extreme environments. Sounds like there's a lot we can still do on Earth, right? There are still quite a few extreme environments. So while we're going into space, sounds like this is a very well-planned and designed endeavor to go into space and provide all the support. So why go into space in the first place?
I think fundamentally it's the challenge of it is part of it, as well as our natural curiosity as humans. And if you look at the way that humanity has spread around the world, we have constantly gone into different and new environments.
Right.
And we have either adapted to those environments, whether it's physically adapted or emotionally adapted to those environments, or quite frankly, we've used our relatively large brain to develop new technologies or new capabilities that help to keep us alive in those environments.
Yes.
And so I think space is to quote Star Trek, is the final frontier on that respect. And the ability to go into space and the ability to learn how to live and work in space has many, many applications that translate back to Earth.
Right.
And so I think it's a combination of our natural curiosity as a species, but also about pushing the envelope about what humans can do and finding ways to adapt or modify those capabilities or technologies for the benefits of people on the ground.
So give us some examples of, what have we discovered in space and brought back. I think telemedicine is one. I believe Jotter pen was one when we were looking to fly high altitude. Which are some other technologies that we have built for space, but now use on Earth on a daily basis?
I think the one that a lot of people like to quote, which is fairly commonly held, is the idea that miniaturization of computer technology came about because of the space program. And so every one of us now has a phone in our pocket that is infinitely more powerful than the Apollo flight computers.
Right.
But everything that we have translates back to that original need or desire to create a miniaturized computer system. And so in many cases, we don't always know what the direct application is going to be of a new technology when we develop it for space flight. And it's only after a number of very ingenious or industrious folks on the ground see what we are doing and find a way to translate it. And an example that I would give you there is actually much of the monitoring technology that we use in hospitals now on the ground in terms of patient monitoring. also came from the work of the initial space program and the Apollo program. And it's the development of those monitoring technologies that enable us now in our hospitals to have millions upon millions of people monitored in the hospital at any given time.
So do you mean the blood pressure and heart rate and things like that, or are we also talking about, what we do on the Fitbits and Apple Watches today?
Yeah, I think that certainly the Fitbits and the Apple Watches are the evolution of that technology over time. But the initial monitoring did focus on temperature monitoring and respiratory rate, heart rate, those types of vital signs were some of the things that technologies were developed to use in the space environment to monitor the health of the astronauts. And that's the kind of technology that has led to our monitoring systems on the ground today, and then ultimately to the evolution of the more advanced portable monitoring devices that we now have, like you described.
Interesting. So monitoring is one thing, but if I imagine myself being, flying into space, there must be many more challenges we face as a human being, physical and mental. So when you are trying to solve for this problem of astronauts in space, how do you frame the problem and what kind of challenges do you really think about?
So from the NASA Human Research Program, we think about the hazards of space as being 5 primary hazards.
Okay.
And we, of course, there's an acronym to everything. So we use the acronym RIDGE to describe those. And so one is radiation. So we know that the radiation environment of deep space has the potential to not only be harmful to humans, but also harmful to all of our equipment and our spacecraft and everything we're taking with us. The I is for isolation and confinement. And that's because we know that as we send humans deeper into space, their spacecrafts are not going to be very large. They're going to be further and further from Earth than any human has ever been before. And they're going to be in a small group of people dealing with very stressful situations. And there's a lot of challenges that come along with that isolation and confinement. The D stands for distance from Earth. And this is the one that my group, Exploration Medical Capability, focuses on, because this one presents the challenge of what happens when you can't speak to the ground anymore. You're too far away to speak real time to people on the ground. How do you make sure that you anticipate all problems before you go and take everything you need with you? Because there's no possibility of coming home and there's no possibility of being resupplied with additional equipment or resources. So distance from Earth is one that we focus on in Exploration Medical Capability. G is gravitational fields or gravitational changes. And this is the almost lack of gravity in spaceflight. We call it microgravity because there's a tiny little bit of gravity, but it's essentially imperceptible. What we don't know about gravity changes or transitions in humans is we have very little data on how we adapt to the moon's gravity, for example, which is 1/6 of the Earth. And we have no information about how we might adapt to the gravity on Mars, for example, which is 3/8 of Earth. So our knowledge of human system adaptation to partial gravity is very incomplete. We have a lot of data now on how people react to microgravity on the space station, because there are people on the space station for 20 years. But it's those partial gravity environments that we need to learn a lot more about. And the last one, the E, is essentially for extreme environments. So how do we deal with the vacuum of space, the temperature changes that come in space, all of the different exposures that we might have as a human to the harsh realities of spaceflight, and how do we adapt to those or develop technologies or capabilities that allow us to best mitigate those effects. So those are the ones that we focus on primarily from from a human research program perspective, but the distance from Earth one is a particular challenge when it comes to medical care.
Right. Yeah. I mean, how do you even simulate the environment, right? A zero gravity, you don't know what radiation will be out there, what kind of forces, what might be flying along the way. So how do you simulate that? Because you can't send a person up there, you can't send a monkey up there and distance from Earth basically does mean, you are very far away. So how do you simulate to do the research?
We do the best that we can in simulating those environments using a number of different analogs. So wherever possible, we try to create an environment that mimics or looks like the space environment or the exploration environment. And so for some of our studies, which are looking at how humans react to isolation and confinement, for example, we have a number of ground analogs where we essentially lock a bunch of people in a tin can for longer and longer periods of time and see how they respond. And so we do some of those here at the Johnson Space Center in something called the Human Exploration Research Analog, or HERA. And we do some internationally with our partners in Russia in a facility called the NEK facility, where we have people that go in essentially for 4 months, 8 months, maybe even a year of isolation and confinement, where they simulate a space mission inside a spacecraft that's on the ground to see how they respond to that environment and the isolation and confinement that comes with it. The ultimate test, though, or the ultimate analog for exploration is actually the International Space Station. And so our primary objective from an exploration medical capability perspective is to try as much as possible to use the International Space Station as an analog for deep space missions.
Got it.
And so we use that. We've done a number of research studies now on the space station where we test different medical technologies or medical capabilities and see how well it not only works in the space environment, but how well the astronauts can perform complex medical procedures in that difficult environment without the support of the ground. So we test their autonomy or their Earth independence with respect to medical technologies.
So does the astronaut then have to be medically trained, or can any astronaut be trained? The technology is so simple.
So the ultimate objective is that we would have capabilities or technologies that anyone would be able to use. Because while there are physician astronauts, there's not always a physician astronaut on the space station.
Yeah.
And so we have developed different types of capabilities where in an ideal world, they might be in the hands of a physician astronaut, but we need to make sure that they are also effective in the hands of a non-physician astronaut. So one of the technologies we developed is a software package that, for all intents and purposes, takes someone who does not know how to use an ultrasound machine and teaches them in a very short period of time how to capture medically relevant images using an ultrasound. And in this case, it was of kidneys and the bladder. And so we have done technology demonstrations on the space station with this software. And we had an astronaut use it who was not a physician. And we did not allow them to speak to the ground while they were using this technology because we didn't want them to get any coaching or guidance. And they successfully, after a number of different runs through the software, they were able to successfully capture very high quality medical images using ultrasound. And so our objective in that test was to show that we could take non-medically trained people and guide them through complex medical procedures without external support. And that's the technology that frankly has many applications in spaceflight, but also has many applications on the ground in remote environments or other places. So it's nice to say that we will push physicians and all these other highly trained individuals into remote areas to take care of people. But what may be more realistic in the future is that we teach people how to take care of themselves, and we give them technology that allows them to do that.
Yeah, so the natural question that came to my mind was, will technology replace physicians at some point? Will robots, trained physician robots, replace human physicians at some point?
So to bring up Star Trek again,
Yeah,
on a TV show called Star Trek Voyager, they had an emergency medical hologram,
right, right.
and that was their doctor, and he
Yeah,
did all their medical work for them. I frankly would be very happy at some point to be out of a job if there was a technology that could do it better than I can.
yeah.
I can say to you that from a technology development perspective, we are a long way away from that reality.
Hmm.
But what I do think we can use, and we will see in the near future, is we will see technology enhancing the ability and the knowledge and the capability of physicians and others, either both medically trained and non-medically trained people. And so as an emergency physician, if I see a new patient in the emergency department and I have to make a difficult diagnosis or come up with a treatment plan for that person,
Hmm.
I welcome anything that will help me to do my job better.
Of course, of
And
course.
so if there's a technology capability or a solution that helps me to make better medical decisions, for example, that's something where the human and the computer can essentially work together to achieve a better outcome than you might have gotten with either one individually.
Right, right. Yeah, and technology certainly as an assistant or assistant is a great thing. But the question that comes to my mind at this point is, so you talked about Ridge and you talked about Hera and other initiatives. But when you look at the human body, I mean, if you look at any machine, for example, look at an airplane in World War II or whatever, you kind of know the failure points, right? That this is what will fail first. When you look at a human being in space, is there any such sequence that this will fail first, or it's very difficult to really map that anything can fail first?
It is very difficult to map that, to be perfectly frank. But one of the things that we have learned is, as we spend more and more time in space, both as an individual spends longer and longer periods of time in space, number one, but number two, as we send more and more people to space, we start to see where those to use your term, where those kind of failure modes come from. And some of the things that we've learned is that there are some adaptations that happen in the human body that we frankly did not anticipate.
I see.
And so one of the biggest challenges we have in space medicine is trying to predict those unknown unknowns. And so we have to, when thinking about our medical capabilities and our medical technologies, we need to not only think about the things that we believe will occur, either because they have occurred in the past or they're known to occur in general to humans, but we also have to think about some conditions that may occur that we did not anticipate.
Right, right.
And so the example that I'll use there is, we had no idea up until a few years ago that people in space could develop blood clots. And it was only through a research project that we were doing, where we were taking ultrasounds of the astronauts and their blood vessels, that we actually found a blood clot in an astronaut. And it was an asymptomatic blood clot, meaning it wasn't causing any specific problems. But just its existence meant that it potentially posed a health hazard.
Big hazard, yeah.
And so that's a great example where we did not anticipate that condition occurring, but we had capabilities and treatment options on the space station that could be used in the eventuality that something like that did occur. And so ultrasound technology is a great example of something where it has many different possible uses. We sent it up for a research purpose initially, but it now has many different clinical indications that we also use it for. So our goal in looking at exploration medical technologies and capabilities are to find the right solutions that meet many different conditions or treat many different problems. Because the more flexible it is, or the more multifunctional it is, the more applicable it may be in the space environment.
Yeah, it's like a universal pill for everything. So that brings me to the question of diagnosis versus treatment. So, I mean, what we have talked about so far is an ability to diagnose, right, through ultrasound, through monitoring of vitals, etc. But how do you send a cupboard of medicine up there when you don't know what you will have to face? And we haven't still developed medicine for everything. A lot of things still happen surgically,
Mhm.
etc. So how do you do that?
It's it's frankly a very challenging problem, and
Uh,
one where, in essence, sometimes in the world of mathematics, it's called an optimization problem.
yeah,
And I know that I can't take everything I want to
yeah,
take.
yeah.
So how do I pick all the right stuff, if you
Mm-hmm,
will, to take with me?
mm-hmm.
And the way that we are trying to tackle that problem right now is using the best available evidence that's at our disposal, as well as some fairly advanced computer models that help us to try and predict which events will likely occur. So we use a technique called probabilistic risk assessment, which
Okay.
is where we essentially run simulations in the computer. We run simulations of thousands and thousands of missions, and we provide a series of inputs on how long the mission is, how many people will be there, and what types of conditions we believe are likely to occur in that mission. And then through running these thousands of simulations, we start to get some risk numbers that show us which conditions are most likely, which capabilities are most useful, which resources are most helpful. And we can use that information to start to create a medical system design that is optimized towards the most likely conditions or the conditions with the highest consequences that we will
Sure.
be able to treat. But ultimately, to your point, there's going to be conditions in spaceflight that we simply cannot treat
Right,
with
right.
current technology.
Mm-hmm.
And so the other thing we have to do when looking at these conditions that may occur is we have to consider not only the complexity of the condition, how well we can treat it in the space environment, but
Mm-hmm.
how much stuff we would need to treat it.
Right, right.
We also have to consider the futility of treating it. On the ground, we will throw every
Everything.
resource at
Yeah,
trying to keep someone alive. But in
yeah.
space flight, you may not be able to do that
Right,
because every resource you use for one astronaut is a resource that's no longer available for another astronaut.
right. So there are
So,
trade-offs.
so some of what we're learning now is that not only is the likelihood and consequence of each condition important, but also the complexity of treating it and the possible futility of treating it helps us to properly scope out what a medical system should look like for exploration.
Yeah, so it's optimization and the resource constraint problem combined. Okay. Now, what is interesting is when I talked to you about failure points, you talked about blood clots.
Mhm.
I thought you will talk about isolation and mental health as the failure point, the first failure point. So why not that, even though it's part of Reg and it's the second thing as part of Reg?
Quite frankly, the challenge that we have right now is that we don't know where that failure point will occur in the human psyche with respect to isolation and confinement. And
Mm,
it's simply because we have, in the history of humanity, we've sent 24 people to the moon.
yeah.
12 of those people have walked on the moon,
Hmm.
and most of them have been gone for a week, maybe 10 days.
Right. Right.
We have never sent anyone into deep space for months and months at a time.
Hmm.
We've never sent anyone on the way to Mars where they reach a point where they look back home and they can't see the Earth anymore. And so we frankly don't know how the human psyche will respond to that. That's one of the great unknowns that we have to consider when thinking about the design of these exploration systems. But the other thing that we do from an astronaut perspective is astronauts are very highly selected. They
Of
go
course.
through an incredibly rigorous process to identify the people who are most mentally and physically fit to
Good.
perform that task. And then they go through years of training to
Mhm.
prepare for it. And so, as much as possible through the selection process and the training process, we try to engineer out, if you will, people who are going to be unable to manage the stress or the challenges of isolation and confinement.
Mm-hmm.
And so we have learned a lot in the last 20 years on space station about how people deal with the space environment for longer and longer periods of time. And our hope is with the new Artemis missions that NASA is going to do to the moon, both in lunar orbit, but also on the surface of the moon, we want to start simulating longer and longer missions, almost to the point where we would simulate a complete Mars mission in orbit around the moon and on the lunar surface, to really see how people respond to that isolation and confinement in the deep space environment.
Right. Yeah. I mean, you talked about the astronauts being, very, very highly trained and inherently very strong, both physically and mentally, almost like Olympians, or even, a lot more than that. But when you think of, the space flights now happening, right, 50 grand, you can be in lower Earth orbit. Yes. But, we are being sold on the promise to land on moon one day, etc. So hopefully Ridge will provide some insight into how a common person who's not fully physically and mentally fit can survive. So is there anything that's happening for the common person as well, or are you still focused on the highly trained and highly selected individual?
In general, I would say that NASA is still very much focused on the highly selected and trained individual, but that's because NASA's focus is on exploration. And the stresses and challenges of exploration are the most severe. But one of the areas that we are working on quite diligently at NASA is the commercialization of the space environment. And so that is focused primarily on low Earth orbit, or space stations that would orbit the Earth. And the ultimate goal is to start to open up space to anyone and everyone who wants to go. And so right now, it's obviously quite restricted based on how much money you have. And a lot of the folks that have the most money also have the least health.
William Shatner is 90 plus, but he's
exactly.
going there. Yeah.
So what we have to do ultimately is, as we develop new capabilities and new technologies for exploration, we're going to have to modify or adapt those for when we want to increase access to space for other people. And so for example, the European Space Agency is looking at who they select as their new astronauts, and they're considering people with different abilities for that purpose. During the Inspiration 4 mission that just happened a few weeks ago, someone flew to space with a prosthesis. That's never happened before. And one of the companies that does zero gravity flights is flying a number of people with different abilities that they're calling their ambassadors. And they want to see how these people of varying abilities adapt or modify to the lack of gravity. And so I think that what we're going to see over time is this increase in the number of people who can go to space, hopefully. And as we push out further and further as a species, we'll start to broaden the envelope of who we can bring with us. But those folks who are at the pointy end of the spear, so to speak, with on exploration, for at least the foreseeable future, are going to continue to be highly selected and highly trained.
Right. It's almost like that's the tip of the spear, but as we start to broaden out, the human machine interface seems just undeniable, right? We will have to support the human body with prosthetics, and I use the term prosthetics very, very broadly at this point. Could mean anything from suits to other devices. Very interesting. So before I continue, Anthony and Tillman, where are you right now in your thought process? What questions are coming to your mind?
So Dr. Lehnhardt, first and foremost, thank you for making an appearance on the podcast, or the VODcast as we're calling it. But one thing that you mentioned earlier that kind of piqued my interest was you had talked about the double-pronged problem, right? Kind of the resource constraint and also obviously the human life constraint too. And I mean, at least for me, one would think that as we continue to explore and go further out beyond low Earth orbit, these problems are only going to become more profound and more convoluted. So that just kind of makes me wonder, do you think that we'll see a point where maybe our aspirations are outrunning our hardware, or do you think that we'll always be able to catch up and find a solution?
I appreciate that question. It's a great one. And I think that the reality is that in many cases, our aspirations do exceed our hardware from a human perspective. But over time, we always find ways to overcome those challenges. And so if you look at the first people who went to Antarctica, for example, the majority of people who tried it in the beginning didn't make it and either came home or died. And then after the first few people did successfully do it, we as humans didn't really develop the ability to live there permanently for decades afterwards, because we just had not gotten there from a technology perspective. So I think that if you think about Apollo, it's actually a very similar type of example where we developed enough technology to get there for a short period of time, but we simply didn't have the capability to live and work there for longer periods of time. And the Artemis missions are us returning to that environment, but this time returning to stay. And so I think that the human need to explore and desire to explore, I think the technology will always catch up, but sometimes it's not there quite yet. And I would frankly use, this is probably a bit of an unpopular opinion, but I would use Mars as a great example of that. The challenges of sending someone to Mars are extreme. And if you think about the fact that the moon is about 1,000 times further from the space station than the Earth is, and Mars is 1,000 times further than the moon. So the mission to Mars is incredibly complicated. And one of the things that frankly will make the mission to Mars much more manageable from a human perspective is if we can simply get there faster.
Right.
But the chemical propulsion technologies that rockets generally use today can only deliver so much in terms of speed. And so right now, what NASA is doing is NASA actually has a number of investments looking at nuclear propulsion technologies, because those can achieve velocities that frankly chemical propulsion can never attain. And so the technological leap to something like a nuclear propulsion technology that can cut the trip to Mars in half is the kind of thing that will enable humans to go to Mars and stay there. But until we take that next leap in propulsion, even if we send people to Mars in the next few decades, they aren't likely to stay. It will likely be for short missions similar to Apollo, and then there will be a period of time during which all of our technology will have to catch up before we can go back and stay there for longer periods of time.
That's a great answer. And you kind of just opened up a whole new can of worms with that answer. But I'm just going to ask you a quick follow-up question, if you don't mind. So do you foresee that like maybe over a long enough timeline that we will be able to send people to Mars and eventually terraform it and have society there?
So terraform it is a challenging question, because that requires a technology capability that we frankly are many, I'd say probably centuries away from. So, but I could be wrong. But can we send people to Mars? Can we live on Mars for extended periods of time? Can we develop the technologies and capabilities in order to do that? Absolutely, we can. But I think that we're not going to see people permanently living on Mars during my lifetime, but I hope to see people at least have boots on Mars during my lifetime.
Thank you for
that. Dr. Lehnhardt, thank you once again for coming on. I just have a quick question, because we were talking about it earlier. You were talking about the commercialization of space travel. I want to kind of bring the conversation back to that. And I was curious on your perspective of A, the necessity, or B, maybe the inevitability of a sort of collaborative effort between NASA and, some of the popular private space groups right now. And do you think that there is some benefit to like note sharing? Let's say it feels like we have some of our best minds sort of split up right now. Is there already collaborative efforts? Is there note sharing? Or is this? I was wondering if you could give some perspective on that.
Yeah, I think you're right. We are stronger together in terms of our capabilities. And I would say that in most cases, the commercial companies that are trying to develop a number of different new technologies or capabilities for human spaceflight, all of those companies have some connection or relationship with NASA. So NASA is either a customer of their technologies or a contributor to their developments. And the future of human spaceflight, I think, is very much going to be a commercial and government partnership, especially for low Earth orbit and for near Earth opportunities. Sometimes for the deeper space things, there's not a lot of drive for some companies to develop those kinds of technologies, at least not yet. But the example that I always use is that the SpaceX rocket that flies people to space right now, the Falcon 9, the engines on the Falcon 9, those are NASA engines. That is a NASA design that NASA gave to anyone who wanted to use it. And SpaceX said, I want to use that. And they developed it and they have modified it. And it's now powering NASA astronauts into space. So it's a great example of the technology exchange that can happen between the government and the companies to push us further and further ahead.
Thank you very much. And I have a sort of a corollary to that then. So we talked about how collaboration can help. To what extent do you think competition will help? You think about the space race back in the day, we've all moving quite a significant bit. Do you think that maybe that's what it'll take to get people more focused on this path, or maybe not? What's your take?
My personal feeling is that, and this is probably just my personality, but I much prefer working with people than working against people. So I'm very much in favor of partnering with anyone and everyone who wants to go to space and doing it as a collective effort. And I think the International Space Station is a great example of that. Russia wanted to have their own new space station. The US wanted to have their own big space station. And frankly, we found that we couldn't do it individually, but we could do it together. And it's been one of the great kind of successes of the international community in terms of this partnership that has existed for decades now to manage the most complex construction project in the history of humanity. So I think that our capabilities, if we can partner with as many people as are able to, I think our capabilities will go further because the diversity of opinion and the diversity of thought will help us to come up with new and better solutions to problems.
Thank you very much. I tend to think likewise, but I figured I'd throw that out there.
Yeah, I mean, you talked about partnership with Russia. You talked about the European Space Agency. So is there a lot of concerted effort across various space agencies in deep space exploration?
So right now, the primary international project that is focused on deep space is called the NASA Gateway program.
Okay.
And Gateway is going to be a smaller space station than the International Space Station, and it's going to orbit the moon. And that partnership right now that's working on Gateway is a combination of NASA, the Canadian Space Agency, the European Space Agency, and the Japanese Space Agency. And there are a number of other countries around the world that have signed on to what's referred to as the Artemis Accords, which are international agreements to participate in lunar exploration as a collective. And so I think that the groundwork is there for us developing this international coalition to go to the moon and to have people living and working in orbit and on the lunar surface. And we're going to do that as a larger human community. And I think I hope that is the way forward for not only those missions, but also, for example, for the missions to Mars.
Right. So bringing us back to the topic of medicine, apart from NASA, where is research happening on this topic? Are there centers that are focused on research on life in space, or is it primarily NASA?
So I would say it is primarily NASA because NASA is the one with the biggest need in this area. But NASA has a lot of partners. both internationally, but also at universities and academic institutions around the country. And so for one, I work at the Baylor College of Medicine, and we have a center for space medicine. And our objective is to not only educate medical students and residents about space medicine, but also to help further what we know about the human condition in space and how we can deal with space medical issues. But primarily, NASA is the main driver for most of this work. And through the Human Research Program, NASA actually funds projects around the country on a number of different topics, all related to the human system risks associated with space exploration. So we like to think about, in medicine, we typically break things down into individual body parts or individual body systems. But what we're trying to do at NASA is consider the human itself as a system. And to challenge to come at the challenges and the risks associated with that human system, we have a number of those laid out at NASA. And at the Human Research Program, we have different elements or different groups who are assigned some of those human system risks. And we do our own work, but we also fund external work in a number of those areas. And so in exploration medical capability, for example, we fund work on the development of new laboratory technologies that can allow us to do lab analysis in space flight or in situ. We also have other capabilities that we are researching where we're looking at clinical decision support tools. So essentially computer programs and algorithms that can help the astronauts to make good medical decisions. And we have other technologies looking at how we can monitor the humans themselves and try and predict before bad things happen, try and predict conditions
what's going to happen
and prevent them from happening in the first place.
Right.
And so the work that we are doing in this area and the work that NASA is doing in this area is the primary driver right now for this area of research. But the other side or the flip side of that is that there is an amazing amount of work right now on the ground on new medical technologies and capabilities that have many potential spaceflight applications. And so, for example, so we just tested at NASA, we just flew a device to the ISS, to the International Space Station, that is a point of care blood analyzer for white blood cells. So we can do a white blood cell count and a differential on a lab sample, on a blood sample in space using a device that was developed for Earth. And with some slight modifications and some procedure development, we were able to modify it and adapt it for use in the space environment. So I think that there's a flow of information in two directions. There's a number of capabilities on the ground that we can modify and use in the space environment. And there's a number of new technologies and capabilities that we can develop for space flight that then have many different ground applications.
Makes sense. I'm watching the time. We don't have a lot more time, and I want to be respectful of your commitment here. But couple of last questions. Number one, you talked about how the paradigm in medicine is to look at each body part or a system, but you talked about looking at a human system, from space perspective. So can you just tell a sixth grader what the difference is between looking at it from a human system perspective versus a sixth grader? Versus a body part.
Absolutely. So for example, a heart specialist, a cardiologist, will think about your heart and your blood vessels. And if you have a problem related to your stomach, they will say, go and see a different doctor. Go see a gastroenterologist. And so as medicine has become more complex, we've broken it down into individual systems. But from a human system perspective, especially with space flight, one of the reasons that we have to consider the entire human is because that human is actually part of a bigger system. And that bigger system is the spacecraft itself. And so the environment inside the spacecraft and all of the interfaces between the machine and the person are essential for us to understand. And we can only do that when we truly think about everything that it means to be a human inside that spacecraft.
Right.
And so it's that interface between the person and the machine that we focus a lot of our attention on, because we need to be sure that the human is considered in every part of the design of that spacecraft. And in the past, historically, the spacecraft was designed, and then someone said after the fact, oh yeah, we got to put a seat in there because you have to have a person in it. Whereas what we want to do is we want to integrate the human system into every aspect of the design. So that from the very beginning, that spacecraft is built for people. And so that's why we try to take a human system approach to all of our problems and not break it down into individual areas, because the concern is always that you'd solve a problem for one small system and then create 3 other problems for another system. So if you don't bring the high enough level perspective to the problem, you might end up creating more problems or not being able to solve it at all.
Right. Very interesting. So it's just the framing of the problem itself that change looking at things in space. So when we are on Earth, we are really looking at the body and individual parts and how do we keep you whole and healthy as long as you want. But when you are looking at a human body in space, it's part of a system. And frankly, in that case, it may not be a stretch of imagination to say, if you're part of a system, the next logical step will be that you may need to be modified to become a better part of the system. And so bionics technologies, robotic technologies, all of these may get embedded in our bodies. Is that a fair statement?
I think it is. But before they get embedded in our bodies, we're gonna find ways to modify and use technologies better. And a very simple example is I'm wearing my Fitbit right now, and it's giving me heart rate data. And I have to learn how to use that data effectively to make myself better.
Yeah.
And so in essence, this is a machine-human interface.
Yes, it is.
And so the ability to develop technologies that can help us to not only do our jobs better in space, but also to stay healthy and to prevent illness in space are essential. And at some point, you're absolutely right. Those may end up being implanted technologies, but for now they are wearables or they're environmental monitors. So there's actually technology now that can look at a picture of your face and tell you what your heart rate is, because it can see the pulsations in your blood vessels underneath the skin, and it's 10 feet away from you. So there's non-wearables and there's wearables and there's implantables. And over time, I think we're going to find ways to use all of those different technologies to enhance ourselves as well as our health and performance.
Wonderful. I mean, like I said, we can just go on forever on this topic, but it's been truly a pleasure, Dr. Lehnhardt, to have you and just learn a little bit more about how you are dealing with problems of life in space. Again, our heartiest thanks, and thank you on behalf of Anthony and Tillman as well. And we will be speaking again soon.
It's my pleasure. Thank you very much for the invitation.